Yeah, so let's get back to this. We are arguing that YIT is influenced by any changes in the explanatory variable in XIT, right? But is that dynamism? So is there dynamism there? Sometimes, I'm sure Balaji must have told you this. Sometimes you use lagged values of X, right? Why do you use lagged values of X? So YIT is a function of XI t minus 1, right? Why do you do that? Is that bringing in dynamism?
Yes, sir.
The specification to this, is that bringing dynamism? How? Here also, what we are saying is that the past values of X is affecting
Current values.
value of X. Past value 1 year. We are just taking one lag. So is that really dynamic? Doesn't matter whether it is T or T minus 1, right? Whether it is T or T minus 1, this is not really dynamic. In the sense, it is not telling you how variables evolve over a period of time. Okay, so what is this eta IT? You can study the panel data models.
Individual heterogeneity.
Individual heterogeneity. What do you mean by individual heterogeneity?
Groups.
Okay, so by the way, why do you take the lag of X when you are regressing it with Y? To address the endogeneity issues, right? What do you mean by endogeneity?
With the regress.
Yeah, so we'll explain that part. Okay, let's just go to. Oh, PhD students or faculty? How many PhD students? Okay, so let's not waste time. Let's go to what is. So what I'm saying is that this model is not really dynamic, or rather, our idea of dynamism is that it's an economic system that evolves over a period of. But this model is essentially not capturing that part. Okay, so what kind of a model is this?
Static.
We call this a static model. So this is a static panel. So all the changes in X variable affects Y based on the specification that you give. It's either X T or XT minus 1. Okay. Then how do we make this system dynamic? Is there a way to make the system dynamic? Okay, I'll give you one example. Let's say a firm decides to make investment. Okay. We want to find out what are the factors that possibly influence the investment decision of the firm. We are looking at the investment made by a firm time period. What are the potential factors that could affect the investment decision of the firm?
Of interest.
Rate of interest. Okay.
Profit.
Of interest.
Profit.
Profit. axis.
In research and development.
Okay. What else?
Non-efficiency of capital.
Okay. Just about productivity. Right? It goes on, right? Wages, it could be several other factors. Do you think the past values of investment, the past capital stock of the firm influence the present investment decision of a firm? Think about this. Firm is making a decision to invest this year, right? So to make the investment, they need funds. How are they going to, what are the sources of funds? Retained earnings. Retained earnings or debt and equity, right? But do you think the previous capital stock position of the firm play a role in investment? It plays, right? Now, how do we define capital stock in economics? Macroeconomics, we use the word capital stock, right? What do you mean by capital stock? Amount of money that can be used for capital expenditures. You are trying to create physical assets. Whenever you say capital or investment, we are talking about creating physical assets, any tangible assets. Tangible assets. Now, how many of you do PhD in macroeconomics? How many of you do in financial economics or anything like that? Okay, how do you capture investment of a firm? Okay.
Change in capital stock.
Change in capital stock. That is the way we define what an investment is. So if you want to figure out how much a firm invested this year, find out the change in the capital stock of the firm, to be the country also. Today's capital stock minus last year's capital stock. Change in capital stock is what is investment. So the previous values of investments is what leads to capital accumulation. So if that is the rationale for capital accumulation, then this year's investment depends on previous year's capital stock, which suggests that it depends on previous year's investments as well, right? Because capital stock is ultimately an output of investment process, right? The argument is that the investment that the firm is going to make this year depends on the previous investments as well, capital stock. So, this model, please understand this part, right? I'm sure Balaji must have already covered this part, so that we are all going to be on the same page. This is what we are looking at. This is not moving. Okay, fine. So we are looking at this model. This is the most basic model that we are looking at, and we are considering a composite error term which contains the unobserved heterogeneity effect, and we have a idiosyncratic error, and we assume that they both are independent and identically distributed, suggesting that there is no correlation between the two. Now, dynamic, we use the word dynamic when the model explains how it evolves over a period of time. We take lagged values of X, but lagged values of X does not make a model, a panel model. You must have studied this COEX, Almond's, right? Distributed lag models when you're studying time series models. You must have studied ARDL model, right? All of them are distributed lag models, but in all the COEX, Almond models or distributed lag models, we are taking the lags of the explanatory variables only. ARDL model, on the other hand, uses the lagged values of Y variable as well. But again, that's a time series data, right? That's a time series data. ARDL model is used for a time series data. So there we use the past values of Y as well. There is no I there because it's a time series data. There is only T, right? So this also does not make the model dynamic. Let's come back to our investment story. What we discussed was that today's investment is related to several factors like this. One factor that plays a key role is the past investment as well. The past level of investment plays a key role in today's investment. Think about another thing. Let's look at smoking habits. What are the factors that affect smoking? To put a model, you can put several X variables, right? Work pressure, habit, fears. You can put a lot of them. Now, let's say somebody decides to quit smoking. Somebody decides to quit smoking. What are the factors that would affect the person's ability to quit smoking? Apart from all the other factors, how many cigarettes he or she used to smoke previously also matters, right? You cannot suddenly stop smoking, right? So previously, if you used to smoke 10 cigarettes a day, it's not possible for that person to cut it down to 0 tomorrow. So the number of cigarettes that you buy today will depend on past cigarette consumption as well. The argument is that it is going to come down in stages. Right? So there are several examples like this where your Y variable depends on the past values of Y itself. We call such models as dynamic panel models. So that is the definition of a dynamic panel model, where we are introducing the lagged values of YIT model. We have a set of explanatory variables, but we will add lagged values of Y as well to this model. That makes it so beta 1 yi minus 1 plus beta 2 small plus I plus. This is what we call as a dynamic panel. You understand the intuition behind this, right? So now you can imagine what kind of models, what kind of applications you can have. Wages. Look at how the factory set the wages. Does the wage depend on the previous year wages? Wage depends on firms' profitability, a couple of other industrial standards and others. Past wages also play a role in deciding what is going to be today's wages. Employment. That's basically what I told was the example for a sticky wage. We have a theory on sticky wages, right? The wages are sticky, but it depends on the previous year's wages. So that's that we are discussing. Wages are sticky, it doesn't. Then employment. That dynamic in the sense this dynamism that we are talking about is employment dynamic. Is the current level of employment influenced by previous levels of employment? Okay. So all these are examples of what you call as a dynamic panel model. And when it comes to macroeconomics, we have several such factors. Interest rate, we discussed, investment. So all these factors are influenced by its own past values, along with a set of other explanatory variables. Right? So this is what you call as a dynamic panel, which is essentially different from the static panel that you have already studied. So the question is, you guys studied how to, if the panel is static, you know how to estimate the coefficients, right? Effects, random effects, pooled models, we learned how to estimate coefficients. Now, how do you do that in dynamic panels? Now, just one more thing. We're arguing that there is an autoregressive component. Basically, your YIT is a function of YI t minus 1 very analogous to the autoregressive concept that we use in time series model. Since the y variable that is realized today is not instantaneous, and since the past variables play a role in determining the y variable, past values of y play a role in determining the y variable today, we also call this model a partial adjustment model. Yeah. The panel data model that you studied in the morning session is typically an adjustment model, because any change in x t instantaneously changes yit, right? But here it's a partial adjustment because x t y the changes in yt evolves over a period of time. So the adjustment to the realized value today, yit, it's something that evolving over a period of time. That is the reason why we call this a partial adjustment model. Any questions till now? As long as you understand this model, understood the story? Now, so why do we, I mean, these are some of the examples that we already discussed. Now, I just want to highlight the last part of this. Why do we have this dynamism in the economic systems that we are looking at? Why do we have this dynamism? One reason could be habit formation. A classic example is the case of cigarettes. There is a habit formation. I mean, that's a very simple example to understand what a habit formation is. Then we have adjustment cost for firms to change the wages, or investment. YIT is investment. There is an adjustment cost to investment. There is a cost involved in adjusting. So that is one part. And then there could be some kind of an institutional inertia. Think about a factory where the labor unions are strong. What about your wages? There would be resistance. It's not going to be, so there could be institutional inertia, or there could be the fact that the system itself is learning from the values. So these are primarily the reasons why there is dynamism. So the changes are not instantaneous. It is dynamic, and it is driven by the fact that there could be adjustment cost, there could be an institutional inertia. Typically, we use the word inertia there. Something from the past is driving. Something from the past is driving today's values. Inertia, the concept derived from physics. So there is an inertia from the past values of one. Now, my first question is, can we apply OLS to this model? We need to estimate the coefficients, right? We have a beautiful model here. We want to estimate the coefficients, beta 1 and beta 2. Okay. We want to know how fast. So what does this beta 1 capture?
Between previous and current value.
The relationship between previous and the current variable. If beta 1 is 0,
then there is no dynamic.
there is no dynamic. Beta 1 is equal to 1. If beta 1 is equal to 1, beta xt minus 1 determines beta. Sorry, beta yt minus 1 determines beta yt. Right? So we introduced this. My question is simple. Can we use OLS to solve this dynamic panel data? Can we use OLS to? Why didn't you use OLS in panel data models, the static panel data models? You used fixed effects model. Pooled models, I understand, but pooled models are not efficient. So what did you do? Went ahead doing the fixed effects model or random effects model. Why? Because there is one villain here, right? While everything else changes over a period of time, there is one factor, which is the unobserved heterogeneity effect, which doesn't change over time. So any modeling that you do should get rid of this. Okay. So how do you get rid of this? Get rid of. So if you want to proceed further and estimate the beta 1 and beta 2, the first step should be to eliminate your beta 1. Right? What did you do? You took the D meaning first, fixed effects, subtracted it from yi bar.
Difference also.
Then you take the first difference also. So the two methods that we typically use to estimate the, to remove eta I from the picture. Then you can estimate the model. But when it comes to dynamic models, we have a couple of other problems as well. Now you see this YIT minus 1, right? What is that? Value of Y. So this leads to some violations. If you're having this, YIT minus 1 and this epsilon T, along with this YT, it tend to violate some of the basic Euler's assumptions. You are familiar with the Euler's assumption, but the first assumption that is violated is the we expect all the variables to be exogenous, means it should be independent. But the problem is that when you have a system like this, right, your YIT minus 1 and the eta I is correlated. It is correlated. Why? Why is it correlated? So for a given value of this idiosyncratic error and the given values of X, YIT minus 1 is related to eta I. Or in the sense, what I'm saying is that YIT is related to eta I, right? For every YIT, you will have a eta I. For every YIT minus 1 also, you will have an eta I, right? Because this eta I does not change. You're building a panel data model. You're one remains one. The eta ones remains the same throughout in the model, right? All the X variables will change according to time. We're looking at it as a matrix. All the X variables will change according to here it will be, let's say it will be X1, 1, 2, some K, K1, 1, K1, 2, K1, right? Now there could be another X variable which could be P11, P12, P13. Have a much bigger system here. But here the problem is that this eta I remains the same everywhere. So which means that the YIT, today's value, is related to eta I. The past value of Y is also related to eta I. Right? This is what I'm talking about. It's the same eta. These things are the same. But look at these variables, the other X variables. It changes, right? These X variables change, but the doesn't change. If this is the case, when the explanatory variables are correlated with the error terms, call it heterogeneity. Okay. OLS needs all the variables to be exogenous. So the assumption of exogenous variables are violated. So we cannot go ahead with this model. Yeah. Also, your so this is the first argument that the explanatory variable, one of the explanatory variable is correlated with the error term. So exogeneity assumption is violated. This is the first violation. Is there any other violation here? What are the assumptions of OLS? So exogenous, no homoscedasticity, multicollinearity,
No autocorrelation.
autocorrelation. So is there an issue of multicollinearity here? Did you address the multicollinearity issue in the static panel data models? No, we assume that one of the assumption is that the x variables, the correlation between the x variables are 0, right? That is one of the assumptions. Now, is there an autocorrelation here? What do you mean by autocorrelation? A variable depending on its own past value. Past value. Is there a case of autocorrelation here? Yes. Yes. How?
Based on the past value, we are determining the present values.
Based on the past value, we are determining the. One more thing. It violates the autocorrelation assumption. Why does it violate the autocorrelation assumption? It violates the autocorrelation assumption because YIT is a function of epsilon IT. YIT minus is T minus 1 is a function of epsilon I T minus 1. Right? Since this it's me, if I it's me online.
Oh, I don't think so. They say this, but I can.
No, that's okay. That's okay. What we are arguing is that your what we are arguing is that there is autocorrelation. Autocorrelation between what and what? Your dependent variable and the error term. So is there a covariance between your YIT and epsilon IT? Yes. Is there a correlation between YIT minus 1 and epsilon TI minus 1? YIT minus 1 and the epsilon TI minus 1 will be correlated, right? So YIT and epsilon IT are correlated. So the previous lag also is correlated with the previous year error term, epsilon IT minus 1. But epsilon IT minus 1 is also correlated to the YIT as well. So what we're arguing is that take the covariance of YIT and epsilon IT, and then we can look at YIT minus 1. What we are arguing is that this epsilon IT minus 1 is related to YIT. Epsilon IT minus 1 is related to YIT. Why? Because so this epsilon, that is a YIT. If you write a model for YIT minus 1, YIT minus 1 will be equal to beta 1 YIT minus 2 plus beta 2x IT plus beta IT plus epsilon I T minus 1. Right? Epsilon I T minus 1. So this epsilon I T minus 1 is related to YIT through YIT minus 1. Get it? Yeah. YIT minus 1. If you expand what is YIT minus 1, you will find that it will be beta 1 into YIT minus 2 plus beta 2 XIT minus XIT plus beta IT plus epsilon I T minus T minus 1. Since this YT minus 1 is an explanatory variable in this model, epsilon I T minus 1 is correlated with your YIT. So if that is the case, is there autocorrelation?
Yes.
There is autocorrelation.
There is the mic. So if you will speak there, then they can listen properly.
Yeah. Okay. I shouldn't move around. Okay. Fine. Can you proceed the slide? Okay. So two assumptions of OLS method is violated here. So you cannot use OLS to solve a dynamic panel data model. The next basically what we are saying is that there are two types of persistence in the dynamic panel data model. One is coming from the lagged dependent variable and the other one is coming from the defect. So this is what the endogeneity thing that we explained, and here comes the autocorrelation component that we. What it means is that there are two persistence, two things that like the YITs. So if OLS cannot be applied, what else can you do? So one method is to.
I have a question.
Yeah.
The assumption of OLS is this, that the independent variables, they should be non-random. They should be non-random.
Should be.
Non-random.
So we are discussing all about random. Is that all the variables are random, no?
Yeah, later maybe we will discuss.
Yeah. Ask your question
He
again.
was telling that in the x-axis everything will be fixed. That
Oh,
will be
that way, okay. When you say random, what do you mean? What we try to say is that you cannot predict the next value. In that strict sense, all the x variables are random. I don't know if I understood your question correctly.
To say this thing. For example, we are looking at the impact of income on consumption. So how we will do it? We will look at the income of different people, and then dependent variable will be random because different people, they can have
Yeah, so that is why it is random.
yeah. So in our books there is this assumption also that the independent variables, they are non-random. So
I'm not sure. Just
later
show me that.
yes, later I will come to it.
x-axis, we will be fixing the values.
Yeah,
That's she was talking. So if
Because that is coming from the sample data, right?
Yeah.
What is the next value that you're going to get? See, so what we need is a model that can explain the population. We don't have information about the population, so we use samples. That is information that we have. If one more unit comes into the picture, how can you say that it would be non-random? To understand what I'm saying is, for the given set of information, it doesn't change. But we are using that to explain what is going to happen, coefficients and other things. But when a new I comes into the picture, new individual comes into the picture, can you tell me what will be the income or consumption level of that person? Tell exactly what is that income or consumption level? Cannot. So I don't understand what you're talking about, but all the variables are random in nature. That's the reason why we have a whole statistical procedure there. Hypothesis testing, all the t-test, everything comes into the picture because we are dealing with random variables. Okay. So the OLS cannot be applied. We will see the one of the methods, two methods that you used in the morning session. Can we apply that? The first one is a fixed effects transformation. How do you do the fixed effects transformation? First, we will do the demeaning. Okay. So here what we are doing is, this is the model. We are demeaning the model. We're demeaning the model. This is what you studied in the morning, right? This is what you studied in the morning. YIT minus YIT bar equal to beta into XIT minus XI bar plus epsilon IT minus epsilon bar. This is what you studied in the morning. we will extend it to the dynamic model. That is what is given in equation number 3. So this equation, we are demeaning. What are we doing? We are going to subtract yit minus yi bar. And then you have this beta 1 yit minus 1. Okay. Now, this beta 1 yit minus 1, when you subtract it from the mean value, there is one observation less, right? One observation is less in the case of t minus 1, isn't it? So we are just going to denote it as y bar I dot minus 1, just to indicate that one observation is missing. Okay, that's all. And then you do the rest of the things the same way you did it for the fixed defects model, xit minus xi bar plus epsilon it minus epsilon bar. Okay. This is how we are doing the fixed defects transformation. So we have demeaned this model. Now, is this solving our problem of autocorrelation? Is this model that we are looking at, model number 3 that we are looking at, is that solving the problem of autocorrelation? Come there, but is it solving? Because here you have yit minus 1 minus yi bar dot minus 1. That is still correlated with epsilon it minus epsilon I bar, because epsilon I bar has epsilon I bar has epsilon t minus 1. Epsilon I bar has epsilon I t minus 1. So does the autocorrelation problem go away? Does it go away? Doesn't. You understand that? But okay, I'll explain again. We have done this transformation here. We have demeaned this variable. Okay. Yit minus yi bar equal to beta 1 yit minus 1 minus yi dot minus 1. We are putting a minus 1 here to indicate that since it is it minus 1, one observation is less. That's all we do here. And of course, the rest of the components. Epsilon it minus epsilon I bar. What is epsilon I bar? Epsilon I bar is nothing but the summation of all the epsilons, which includes epsilon it minus 1, epsilon it minus 2 divided by n, right? So what I'm saying is that when even after this transformation, you're observing that there is a correlation between your y, this factor, and this factor, because see, this includes epsilon I bar includes epsilon I t minus 1. So correlation problem, the correlation problem that we were discussing doesn't go away. So within transformation is not helping us to overcome this problem. First difference. Can you try doing a first difference? First difference of this model. Differencing of a model. Remove the problem of autocorrelation. Those night issues that we are discussing about. Can you write the model? You need to write the model. The place where you can make mistakes. How will your FD, first difference model, look like? YIT minus
minus 1.
YIT minus 1. Beta 1 into YIT
Minus 1,
minus 1 minus
YIT minus 2.
YIT
Minus
YIT minus
2.
2 plus beta 2 into XIT minus XIT minus 1. Eta I goes away. Eta I minus eta I is 0 plus epsilon IT minus epsilon I minus 1. Does this solve our problem? What are the two problems? First one is endogeneity. Second one is autocorrelation. Is this transformation solving your problem? The autocorrelation still there. There's the epsilon IT minus 1 there. Is it going away? Yes or no? Why? What is still there? And it is connected to YIT through this XIT minus 1. That is not going away. We are not able to solve the endogeneity problem as well as the autocorrelation problem, fixed effect transformation or first differential. Okay. That part is okay. Is there any doubt till now? Eta I minus eta I is 0. Oh, so that's. So remember that this is a one-way error component model, okay? Because we are using a eta I only, we are not using a mu t. Is that the mu t that you are talking about?
Yes.
Oh, okay. So I just use the one-way error component model. It says that we are looking only at the individual homogeneity effect. We have not looked at the time specific effect. If you want to model it fully, you add a. Okay. I just ignore that part. The assumption is that that is getting captured here. Okay. Okay. Now, even after doing this transformation, we are not able to overcome these issues. The YIT minus 1 is correlated with the error term. So if YIT minus 1 is correlated with the error term, then the estimates will be biased and consistent. Right? Now, this is what you call as nickel bias. This is what you call as nickel bias in the context of a panel data model. This typically comes into the case where we are dealing with a micro panel. What is a micro panel? A micro panel and a macro panel. What is a micro panel? More, T is more or N is more, T is small. That's a micro panel. Macro panel is opposite. Opposite. This nickel bias typically comes into micro panels where you have less number of observations. So if you are looking at a linear data compared to a data that has 30 years of observation or patients, the bias that comes with even after doing this transformation is what we call as the nickel bias. Okay. So the Bipin transformation and the first difference transformation doesn't solve our problem. That doesn't solve our problem. And this is the case of your, this is what we have written on the board. Doing this transformation doesn't help us because your YIT minus 1 minus YIT minus 2 is correlated with epsilon IT minus epsilon I minus 1. See, these two are correlated. These two appear there. So it doesn't go away. Okay? So both these methods doesn't help us. So, and the famous econometrician, he calculate the value of the bias as 1 by T. So if your T is small, the bias is This is higher. So if you have a higher T, if it is a macro panel, this bias might go away. It might not be a concern for you. But micro panels, which is the typical macroeconomic panels that we get, they face this nickel bias. Okay. So what happens here is that when there is nickel bias, we tend to underestimate the persistence of beta 1. So what do you mean by persistence? There are two types of persistence that we talk about. Of a correlation that is leading to some kind of persistence. Now, what happens is that nickel bias typically leads to underestimating the persistence of beta 1. Why? What the oilless does is it overestimates it. Oilless overestimates the bias. The fixed effect transformation as well as the first difference transformation is going to underestimate the bias. So where will the true value of beta be? So what I'm saying is that if you run a dynamic panel model using oilless regression, the coefficient of this variable, coefficient of this beta 1 will be higher, will be overestimated in the case of oilless, and it will be underestimated in the case of fixed effect transformation. First difference or a fixed effects transformation. Even when you compare it between fixed effects and the first difference transformation, this bias is more in the case of first difference transformation. So your oilless estimates are biased and consistent. So you cannot do that. So what econometricians do to overcome these problems constitutes the dynamic panel data models. Okay. Techniques that we use to overcome these issues is what we call as the dynamic panel models. So what we have described till now is one, what are dynamic panels? What makes a panel dynamic?
Values of dependent variable.
Huh?
Lagged values of dependent variable.
The current the YIT that we are looking at depends on its own past value. Economic systems evolve over a period of time. We discuss some examples as well. Smoking, investments, wages, employment, all depends on its own past values, right? So that kind of a model cannot be estimated through the conventional models that we are familiar with. We use oilless to estimate that kind of a model where your YIT depends on YIT minus 1. Then we come across several issues. The estimates that we get are all biased and inconsistent. It comes from the fact that endogeneity issues and there exist correlation. This leads to bias in the beta coefficients that we estimate, the beta 1 that we estimate. We are doing this dynamic panel using an oilless regression. Bias arises, which leads to overestimation of the model. Beta coefficient that you will get will be higher. Okay? Because there is a positive correlation there. So if you look at this, there is a positive correlation between your YIT and IT, and then here if you are looking at the first different transformation, there is a negative sign, so it's a negative correlation there. Okay. So in the case of oilless, the correlation is positive, which leads to overestimation. Here it's a negative one, it's a differencing, right? The relationship between the two is negative, so there is a negative correlation between the two. So this model typically underestimates the beta coefficient, beta 1. So if I run a model, let's say we are looking at the case of investment, I find one beta through oilless. It is overestimating. So this turns out to be the upper limit for us, because we know that it has overestimated it because of the positive correlation between your Y and error. Then when you're doing the first difference transformation or effects transformation, that leads to an underestimation of the beta coefficient. So you get a lower bound as well. What should be the real value of this beta? It will be between both. That's the right answer. It is going to be between both. Both the models overestimate and or underestimate. What we need to find is a model that don't do. In that case, the model that we are going to find will give you a beta value, which is between the upper bound given by OLS and the lower bound given by its effects model. Okay. How do we do it? So there comes the first model we call as the Anderson-Hazao estimator. The first model that tried to explain this issue, this particular issue. What it does is that it uses instrumental variables. It uses instrumental variables. What are instrumental variables? Yeah, so in a simple setting, let's not get into the dynamic model. In a simple OLS model, what we want if xi and epsilon I are correlated, you try to find an instrument which is correlated with x but not correlated with epsilon I. Problem is between the error and the explanatory variable there. So an instrumental variable is nothing but a variable or a vector. If you are looking at it in the vector notation. How have you studied OLS models? Have you used the metrics method to derive OLS? Ordinary least square method, or did you guys just use the sum of square? Gujarati. Which textbook did you study for OLS? Gujarati. So you can do panel data models using the metrics method as well. You can look at Brooks. They use that method. Woolridge also in some versions. Think about this data as a matrix. So y error components, yi minus y hat. This error component. Think about this as a matrix. That makes it a lot easier. I studied econometrics using Gujarati. So very difficult. But when I started using the metrics model, it became intuitively more clear. Then when I taught econometrics, I did not touch Gujarati. Switching them using this metrics method. And believe me, go back and try to derive the OLS estimates using the metrics approach. Makes a big difference because I firmly believe that once you have the intuitive understanding of how this data looks like and how the transformations change the data, it's much easier for you to understand what is going on behind the scenes. And we are going to use some metrics approach also here. So what Anderson and Hazao do is they use the ID approach. They are going to bringing an instrumental variable. The problem is that in a simple OLS model, not a dynamic model, a simple OLS model, xit and epsilon it are correlated. Okay. If they are correlated, find an instrument which is correlated with x but not correlated with epsilon. That's the basic idea. So if we apply this to dynamic panels, what do we need? What kind of an instrument do we need? We're not concerned about this x part at all. We're not concerned about x part at all. Reason is that we assume that all the x variables are exogenous. Okay. A strong assumption, but all the variables are exogenous. All the x variables are exogenous here. So we are really not concerned about the relation between xi and epsilon I. What we are concerned about is the relationship between yi minus 1 and theta. Okay. Now, so if we have to use an instrumental variable, how will an instrumental variable look like? These, right? What does it look like? Write it as a matrix. How will it look like? Huh?
There will be one column.
There will be
One column and
only one column, or can there be multiple columns? So Start thinking like this, okay? Y1, 1, Y1, 2, Y1, 3, Y2, 1, Y2, 2, Y2, 2. Right? Is equal to?
Sir.
So they are saying that.
Wow.
If I stand here, can you guys hear me? How will your yi t minus 1 x matrix? This one, then y1, y12, y13, y14, it goes on corresponding to this. Then y2, 2, because we are taking y t minus 1, right? Then y23, y24, and it goes on, right? How will your x look like? Assuming that there is just one vector. So y12, for x12, x13, for x11, x12, x13, x21, x22, x23. Because once you have the error term, how will it look like? Epsilon 11, epsilon 12, epsilon 3, epsilon 21, epsilon 22. For this framework, okay? Our problem is that
There will be y10.
y10, ith observation, time period 1.
Period 1.
So it will go up to time 10. So this is, I should put a comma here. What it means is that ith observation in the first time period. It is y related to the past value of y. So if you are forming a data, like if you open data, go to data editor, once you do this transformation, this is what you see, right? Now, Anderson and Hisayo argues that one way to overcome this bias and inconsistency in the OLS or the fixed defects estimates in dynamic panel is to do some instrumental variables. Instrumental variables are something that we use in OLS models. The basic intuition is that the X variables are, so if you are having a model like this, right? This is, have you studied instrumental variables? Yes or no? Okay, it's a simple OLS model, right? What it means is that there is a correlation between X and the error term. You need to find another variable, let's say another matrix Z, okay, another matrix Z, which is related to X, but not related to epsilon. See, now we have solved the problem, right? Now we have solved the problem. This is what Anderson-Hisayo model does. In fact, all the dynamic panel data models use this approach. They come up with different instrumental variables to overcome this problem. Is that part clear, or any questions? Okay, so what it does is it creates another instrumental variable. How will this instrumental variable look like? What is the nature of this instrumental variable? The nature of this instrumental variable. I did not put anything here. Why didn't I put anything there? That is what matters, right? So what Anderson and Hisayo suggest is that you use yi t minus 2 or delta yi t minus 2 as an instrumental variable into the model. See, the problem in the dynamic model is that there is a correlation between these, right? The past values and the error term. You need to overcome that. How do you overcome that? One approach is, well, take the change of YIT. Delta YIT, what is delta YIT minus 2? Delta YIT minus 2 minus delta YIT minus 3. So there is no epsilon I t minus 1. There is no correlation between epsilon I t minus 1 once you do this transformation. What I'm saying is that here, the instrumental variable that corresponds to x would be delta yi t minus 2. Okay. What is that? Delta. It's a change, right? It's a change. So it does not change much, right? So what we do is we use this kind of transformations to create instrumental variables. And when we start doing the operations, the multiplications eventually to derive your beta hat, we use the instrumental variables that will help us to overcome the previous problems that we discussed. Clear? Then the second model, Anderson-Hesseau model is a very basic model. It comes with a set of limitations, or rather it has more limitations than the actual applications. It just uses the delta YIT minus 2 and using just one variable in the Z matrix, the IV matrix, does not really help. That is where Arlano and Bond comes with another model where they say that they take the first, what they do is they take the first difference to remove the fixed defects. Then they use the lagged levels as instruments for the difference lagged dependent variable. It might look complicated. Once we write the model, it will be a little more clear. I will explain each of them in detail. It takes the first difference to remove the fixed defects. That is the first step. Okay. It could be meaning of first difference, but an Arlano bond uses first difference. So you remove the fixed defects first. And after that, what you do is use the lagged levels as instruments. What you find in Z will be the lagged values of the level variable for the first difference lagged dependent variable. So we will write the model so that you have it. Then comes the, well, this also comes with a certain set of issues. Okay. Have you studied method of moments? Method of moments. So when you, how do you estimate the beta coefficient in an Euler's model? What is the method that you use?
Minimize this.
So minimizing it's a minimization problem, minimizing the sum of squares. There is another approach to find the beta coefficient, which is what you call as the method of moment. Which is the first moment when you are looking at mean? Second, variance. Third, unus. So what we do is we don't go beyond variance. We use typically the first moment, that is mean. In the method of moments, what we try to do is we try to minimize the mean value. I will explain that. But method of moment is another approach that you can use to estimate your beta coefficients. Just like how you used minimization to reduce the sum of squares to estimate the beta coefficients, you can use method of moments as well. That is again a minimization exercise. In fact, in all the models that we discuss, it is all minimization problems. Okay. So Arlano bond, this is what they use. They use the lag levels as instruments for the difference lag dependent variable. It had its own sets of limitations, or what Blundell and Bond and Arlano and Blundell later comes up with another paper where they add some more instrument variables. What they do is they used lagged differences as instruments for levels. We will write the specification. You will get a little more clear. Okay. So the whole argument is that system GMM turns out to be much better if there is persistence in the y variable, the y t minus 1. Okay. So this is what we do. There are maximum likelihood and bias corrected LSDB method, least square dummy variable methods as well. But our discussion is going to be around these two. Okay, these two, the most commonly used approach. Take a break.
We can have a tea is arranged out.
The session is till what time?
Today's.
Five
Till,
to-
this session is till 3:30. We planned for till 3:30.
Okay.
So we can-
Any questions? Are you following what I am saying? Yes?
Sir,
Oh, yes.
excuse me. Sir.
Yeah, tell me.
Sir, may I ask one question?
Yes.
Sir, can you just explain what do you mean by the persistence of the dependent variable? I'm not getting it.
Okay, so I will explain it with an example. Okay. We argued that today's investment, if the YI looking at is the investment that is realized today, depends on previous year's investment, right?
Yes,
Can
sir.
you hear me?
Yes,
Yes,
sir.
right? To what extent does the previous year's investment influence the current investment? That is the simplest way to think about persistence. Okay,
Okay, sir. Okay, sir. Thank you, sir.
understood that logically, right?
Yes, sir. Yes, sir.
Does this YIT influence the -1? This is what matters to us. Okay, so if there is persistence, any other questions?
Sir.
Yeah.
First of all, sir, good afternoon, sir. Sir, I want
Yes.
to ask the question. Sir, I want to ask the question, but the question is a little bit out of this topic. I want to ask that why do we use interaction term, sir, in panel data analysis?
Okay, well, that doesn't come under the scope of this, but one, it depends on the nature of the question that you are looking at. Okay.
Okay, sir.
Is there
Yes,
any
sir.
specific context that you can tell me so that I can try to explain it?
Okay, sir. Fine.
Is there any context in which you want me to explain it?
Women and village.
No, sir. No, sir. Just I have read the literature of panel data, sir. So for some variables they take interaction term and all that.
Okay, so the reason is that why do we have this interaction terms? What do we, a simple interaction term, why do we have this interaction term? The reason is that when you have variables that are related, right, there could be some influence.
Yes, sir.
So, the simplest way to look at and construct an instrument variable will be to just find the product of that. That will eventually capture the variation because of the coming from these two variables.
Okay.
So,
Okay. Thank you, sir.
let me see if I can explain it more intuitively.
Okay, sir.